I'm very excited to introduce our first speaker of this program, Jibran Rashid. Jibran Rashid is a board member at QWorld. He did his PhD in computer science at the University of Calgary, has a Bachelor of Science from Carnegie Mellon University, is now an assistant professor at the Institute of Business Administration in Karachi, and he has taught thousands, maybe 10,000 people, meanwhile, Jibran, in quantum computing and programming. He has been there from the start of the Womanium Global Quantum, now the Womanium Global Quantum and AI program, exciting everyone and teaching everyone in the basics of quantum computing and programming, and then more the advanced parts, quantum algorithms with QNickle. Back last year with many people happy that you returned. And now, for the third time, you are here. We are extremely excited to always have your support, always have your great insights and interactive lectures. And thank you for joining this time. Excited for your first lecture on QBronze.
Thank you very much, Fumi. Marlou, thank you very much, everyone. I'm hoping that, yeah, I've done 10,000, but I'm not so sure. So yeah, let's see. Hopefully we'll get there as well. So unfortunately, this time around, I'm only doing 2 lectures right in the very beginning for QBronze. And as Marlou already mentioned, you've got like a wonderful program ahead of you. Much of the content I'd love to be part of as well. But I'll be only running the first 2 lectures today and tomorrow. I saw a lot of questions on Discord already about, some people being slightly anxious about what to expect. And I guess one kind of advice would be to take it as it comes your way and just kind of try to do the work as it comes. So we've had students who have done similar programs, not exactly the same one, obviously, over previous years, where there were high school students who had background knowledge, or maybe in some cases not even prior programming knowledge, and successfully completed the entire workshop, and even kind of the people who are leading in terms of success at the end of the workshops. So just do the content as it comes along. It's definitely work. It's a reasonable amount of work, but it's nothing that you shouldn't be able to do if you just put in the reasonable amount of time required for it. And so with that, I'll just quickly summarize some more details about what we'll be covering in this kind of bronze workshop. So bronze, if you're not familiar with QWorld, is kind of our introductory workshop on quantum programming and quantum computing. Many of you might have already done it, in which case, as Marlou already mentioned, you don't really need to do this, but it would be great for you to be able to participate on Discord as well, maybe answer questions and queries from new students. The format of this bronze workshop is slightly more concentrated than the previous sessions that we've had. As you can see on the screen, which is essentially the Canvas login page, a landing page, we essentially have kind of 3 lecture sessions. The first session today will kind of run you through about 2 days worth of sessions on the QBronze lectures. And then the second lecture tomorrow will again be worth roughly 2 lectures from QBronze. So QBronze is usually 5 days of content. And so you've got kind of 4 days of content roughly packed into the lecture content, at least, packed into the first 2 days. To make up for that, you've got kind of an exclusive tutorial session then on June 5th, led by Claudia, our coordinator from Q Education in QWorld. And she'll be running you through an actual hands-on tutorial, getting started programming in Qiskit, the IBM quantum library. So if you haven't had a chance to do quantum programming before, but you know programming, then this would be kind of a great hands-on experience for you to actually get started doing the programming. My sessions will be a bit more theoretical, so I'll try to get you started and get you up to speed with all the theoretical content about this workshop. And then the June 5th session will be all the hands-on training that you need to actually start the programming. I'll talk a bit more about that. And then the June 7th session on Grover's search is kind of self-contained, gives you kind of complete introduction to one key quantum algorithm known as Grover's search algorithm. And so that will round off our content, at least in terms of lectures, for the QBronze. Similarly, as Marlou mentioned, there's the QNickle, there's the annealing workshops, which will be, and different other workshops that will be upcoming in future weeks. But these kind of 4 sessions round off the QBronze workshop in of itself. So there's nothing else that you need to do in terms of the lectures for QBronze. For sure, they are the corresponding exercises and modules that you'll need to, assignments and quizzes that you'll need to do for QBronze. All the questions and in the assessments for QBronze are essentially multiple choice questions or simple one-line, two-line kind of programming answers. So if you have done the work related to those assessments, the assessments are essentially questions that you would have already seen before, and it's just basically figuring out the new number, do the same calculation to figure out the new number that goes in. Now, what exactly is the learning content that we are using for these sessions? If you go to the QWorld website, it has a link to QBronze, and it takes you to this GitHub page for the Bronze Qiskit. What this is kind of a self-contained set of Jupyter notebooks that introduce all of the content using Python and Qiskit. So even if there were no lectures, the idea behind these notebooks is that a self-motivated student could work through these notebooks. If you open up these notebooks, you'll see that they contain kind of really detailed explanations in addition to programming exercises with solutions of all the topics that they discuss. So don't take the lectures as be the kind of one and all thing about the lectures, about the content, but rather these notebooks really are an essential component that go hand in hand with the lectures. So the idea is you see the lecture, maybe not live, you see a recorded version of the lecture, then you go to the corresponding set of notebooks for that lecture, and then really the expectation is you work through the notebooks. You see the explanation, you see a worked out programming example, then you write down another programming solution yourself, and then through that process, you really kind of hopefully get a better understanding and appreciation of that content as well. All right. We are using Qiskit version 1.0 starting from this workshop. So if you go to the QBronze webpage on QWorld's website, the new GitHub repository does use version 1.0. So we're not using version 4.46 anymore. So if you have an older repository downloaded for QBronze, I do recommend to download the newer version, which is just available using the same link. It uses Qiskit 1.0. That's essential because all the assessment solutions also now assume that you're using Qiskit 1.0. All right. And Claudia hopefully will kind of do lots more explanation of this during her tutorial as well. I'll share this link over here in the Zoom chat as well as in Discord, but I think we will hopefully be able to post it in Canvas as well so that everyone can kind of see it. All right, so I posted the link in Zoom chat as well as in Discord live Q&A. All right. Any questions so far? Any concerns? So yeah, really love if people can just ask questions right on the spot in the chat or on Discord live Q&A, or just unmute if that's possible as well. All right.
There is a question. Can we also use previous versions of Qiskit, or do we need to use Qiskit 1.0?
Right. So I do strongly recommend, in fact, essentially, yeah, you should use 1.0 because the idea is the assessments have been updated to assume. So for example, for a programming question, the idea is you would be using the library call corresponding to 1.0. So you end up with a solution that would be correct for the prior version, but then for Qiskit 1.0, it wouldn't work. So you should use the Qiskit 1.0 version for our current iteration of Bronze. Yeah, version 1.0.
The link that Jibran just posted is also available in the Get Started QBronze. So if you just go, start with 1.0, you will see all information there. Then there is a question, Jibran, what kind of pre-knowledge do I need? Are there any requirements to successfully start with QBronze?
So the usual prerequisites that we identify are some basic prior programming experience, perhaps in Python. But even if you haven't done programming in Python, maybe in some other programming language. And then within the Bronze Qiskit repository, you'll identify a brief tutorial that gets you started on the syntax that you need for Python. So we definitely don't use everything that's available in Python. You just need a very basic subset of libraries. So if you've done prior programming in any other programming language, it should be relatively straightforward to get started in Python. But a bit of programming experience is definitely useful. If you are learning quantum and programming both at the same time, that definitely can get daunting. I'm sure there are some people who have successfully done that, I wouldn't recommend it though. Like they're two kind of relatively kind of conceptually challenging tasks to do together. So I would say have some prior programming experience, or even before. So this is not to say that, hey, stop doing bronze right now. Just take a day or two to get familiar with the Python tutorial that's available in Bronze Qiskit. And once you're familiar with it, then it should be possible to get started actually doing the programming exercises in Bronze. Another key mathematical requirement would be linear algebra or matrix algebra. So we assume familiarity with matrices, multiplying matrices and vectors, inner product of vectors, things like that. Again, some basic tutorials are available within Bronze Qiskit, but the more familiar you are with that, the better it is. I know of no active research scientists within quantum computing or any active technical field who would say that they know enough math. So yeah, you could always know more math. But in terms of getting started with Bronze, just some basic familiarity with matrix algebra and programming. Those, I think, are the key technical requirements. All right.
Yeah. Then, Jibran, could you share the canvas on your screen and go to the
Sure.
1.0 Get Started QBronze installation and test? Yeah. So to this module, you will go to the left
right.
up and you will see modules there. And then just to show to everyone, scroll down.
Get started, Bronze.
1.0 Get Started QBronze installation and test. This one will be available after you did the pre-course survey. And here you see an overview of the course materials that will be available for this first module for QBronze. One is the lectures. There will be 3 lectures and a tutorial provided today, tomorrow, Wednesday, and Friday. Second is exercises, these downloaded Jupyter notebooks from that Bronze Qiskit GitHub link that Jibran showed. And those are for your own learning and understanding, but very important. So go to this GitLab link, download those exercises and do them. We won't see what you do there. We will only see it in the quizzes that you complete. That number 3, complete the QBronze quizzes. And could you also show one example of that, Jibran, and where we can find those?
So
if you go back to modules, yes, then you
so here are the quizzes.
Exactly. 1.1 through 1.5 are the quizzes to test your knowledge. There you need to score at least 10 points in each quiz, 50%. And 70% of the whole module, so for these 5 quizzes, you need to have 70 points. And then you can pass the module. For those who have already done QBronze before with QWorld or with QWorld in the Womanium program, you can upload your previous certificate here in this one exercise. If you upload it there, you will get 1 point. That 1 point is symbolic. It is just for Womanium team to see that you uploaded it. I see questions about it. Don't worry about it. If you have 1 point, we see that you did it before. If you have 0 points, great, then you can do the subsequent quizzes. You can attempt each quiz 3 times. Is that right, Jibran? And the highest score will
I think
count.
so, yeah. Usually that's the requirement. Let's quickly verify that as well.
Then there is a question, can we upload the certificate and still do the quizzes? Yes, we highly encourage that. It is great to practice. You just won't get a new certificate because you already earned it before.
And the quizzes, I don't think really are, the questions really are very similar to Bronze workshops that you've done before, perhaps. So if you already have a certificate, it's not really as if we have created new assessments here. So most of the questions are really very similar to what you've seen before. But for sure, if you want to do the quiz, that's great. All right. So people who haven't seen this before, perhaps. This is kind of what the landing page of the notebooks looks like for the set of exercises that what I and Marlou have been talking about. So you notice essentially all starting from kind of basics of classical systems. That's where the actual technical content of the workshop actually starts. Before that, you've got kind of the prerequisites coming in from basic math and programming. When I mentioned the first 2 lectures, that's essentially content covering basics of classical systems, basics of quantum systems, quantum operators, entanglement, and protocols. And then the last lecture will be Grover's search algorithm. In between, we'll have the tutorial that will give you the general overview of how to get started programming using Qiskit. All right. There's no requirement of which IDE you are required to use. You can, whichever one you are comfortable with. The one that we strongly recommend that we kind of work with already is kind of Anaconda for Python. But if you have a specific IDE that you prefer, that's perfectly fine. Right. So the lectures, hopefully, fine. Yeah. So yeah. Which one did I miss?
And then there is the last question about the due dates. You see that the advised due dates are very tight. It is set to tomorrow to try to get started, install QBronze, and then for the day after on Wednesday to do this first quiz on the basics of classical systems. These are recommended due dates because they prepare you for the next lecture. The final cutoff, for which we will see if you completed the quizzes with 50%, is June 23rd. Yeah. So if you see you need to catch up more with some linear algebra, with some programming, no worries, you have time.
Right. And then just for kind of bronze, just because we've condensed the content and you don't have prior Qiskit programming experience, perhaps it would be reasonable to wait until you have seen Claudia's tutorial, such that you've seen kind of a hands-on practical experience with Python and Qiskit together. Because the first 2 lectures, yes, will give you lots of theoretical content, but you won't get a chance to see too many hands-on programming examples that you'll see during the tutorial. So it's perfectly fine if you kind of take a day or 2 to get familiar with that after the tutorial, and then get started with the quizzes. You should still have ample time to get done with by the deadline of June 23rd. All right. And then essentially, once you downloaded the repository from here, I would recommend working on it locally. Is this how it is supposed to look? Let me quickly verify. So there, that you're in the collaborations page, right? But yeah, you seem to be on the Womanium Canvas page, Rafael. All right. Any questions about kind of these logistical issues and concerns? For sure, we'll be available moving forward to answer these queries as well, but hopefully this is enough to get started with the actual fun content. No major queries. So perhaps we'll actually get started with actual fun content. So let me just change my screen.
And feel free to take your time, Jibran, until 1 p.m. ET, which is, yeah, then also the follow-up.
Awesome. You got some time. All right, so let me stop sharing.
For anyone asking about links, Canvas links, other links, please look into your welcome email. If you have just signed up and haven't received welcome email yet, it will follow within the next 2 days. Then we will start the first lecture on QBronze.
All right. So if you've heard these jokes before, please, I'm sorry, you're coming here for the same thing again, but yeah, it's really my favorite joke as well. We are getting started now with the first lecture for QBronze. The idea is I want to give you an overview of what to expect to see in the field of quantum computing if you're coming to it from any other field of kind of technical field. And especially that my own perspective comes in from a computer science background. And so many of the details within the QBronze workshop and the QNickle and quantum annealing workshop as well, all have been designed with a kind of a computer science perspective in mind. Having said that, it is completely possible to look at all this content from a different perspective as well. So think about quantum computing from a physics background, from a mathematics perspective, from a philosophy perspective. Unfortunately, that's not what we are able to do right now within the QWorld workshops. What we are providing you is kind of a quantum computer science focused perspective on quantum computing. So the joke goes, an engineer, a physicist, a mathematician, all 3 of them check into a hotel for a night. They are all assigned a room. They're all kind of identical rooms, and they check in there. They're tired after maybe a big conference day and go to sleep. And now it just happens that at nighttime, the engineer's curtain in the room catches fire. The engineer gets up, goes to the washroom, fills a bucket of water, throws it on the fire goes out, all's good in the world, goes back to sleep. Now, it just happens that the fire in this time has passed on and continued to burn on the physicist's room's curtain. The curtain is burning. The physicist gets up, sees the fire, goes to the washroom, sees a water hose, sees a tap, quickly sits down and does a back of the envelope calculation to figure out what's the optimal angle to incline the water hose at that will minimize the time in which the fire will go out. Does that calculation, gets the answer, connects the hose to the tap of water, turns it on, inclines the hose, the water comes out, the fire goes out, all's good in the world again, goes back to sleep. Now, as you might expect, the mathematician's curtain catches fire. The mathematician gets up, sees the fire, sees the water hose, exclaims a solution exists, and goes back to sleep while the fire keeps burning. And so that is, some element of truth to it in terms of how these three different fields approach kind of the problems that they're looking at. For sure, it's kind of caricaturized, but, hopefully we'll see some of that element in some of the discussions that we'll have as we move forward. Okay, so now, given that we have done this, let's kind of ask a more fun question. What's your favorite superpower? So shout it out, put it in the chat. Maybe if you want to give an explanation as well in terms of why that's your favorite superpower. Invisibility, awesome. Time travel, teleportation. There's always teleportation in there, but maybe it's the quantum teleportation. Entanglement is your favorite superpower. Hey, that's like you're kind of 5 steps ahead of us. Vivid dreaming, flying. All right, vivid dreaming. All right, so whatever you dream comes true. Alrighty. Programming and technology, reading minds. Did I miss something on Discord? Share manifestation. I'm not sure I know that one. Antonio, could you tell a little bit more about share manifestation? Web shooting, Spider-Man's here, super genius, perseverance, critical thinking, exploring all the hidden mysteries of nature, upload consciousness to quantum systems. All right, excellent. There's lots and lots of stuff in there. Okay, so hopefully by the end of my session tomorrow, I'll try to hopefully also tell you what kind of favorite superpower I have in mind and motivate it in terms of answer as well. The one that I had in mind had something to do with this kind of X-Men or X-Woman. Good bowel movement, interesting. Okay, so any ideas with, so what I'm getting at with this kind of slide was luck. And if I want to claim or state luck in a more technical way, the ability to manipulate probability. And perhaps I'll be able to convince you by the end of our session tomorrow that, well, maybe slightly because I won't do all of bronze, that quantum computing exactly provides us kind of the best possible approach that we know so far of actually getting this superpower of being able to manipulate probability in a way that classical physics does not allow. And that's essentially one way to understand quantum physics and hence also quantum computing, that we end up being able to manipulate probability in a richer way than what was otherwise possible. And so that in some sense is the most realistic superpower that we have access to in some sense, right? But for sure, I'm kind of biased as well, given that we are talking about quantum computing. Alrighty. So given that we want to talk about quantum computing from a computer science background, all the Harry Potter power, that one I missed. All right, okay. Very much like physics, whenever you got introduced to kind of physics, you got introduced to Newton's laws of motions, motion, not motions, and you got kind of this idea that all of classical physics, at least mechanics, is kind of built on those laws of motion. So if you wanted to think about computer science in a similar way, hey, here's the kind of foundational bedrock of computer science from which most, if not all, of computer science emerges, what would that be? Unfortunately, our kind of field of computer science is still relatively young, so there might not be as much a consensus in terms of what that foundational bedrock is, nor is it kind of as popular as Newton's laws of motion. And so one of my goals with this lecture is to kind of make sure that people kind of get a better understanding of how computer science, classical computer science, quantum computer science links to that foundational bedrock. And what I'm referring to is what's referred to or stated here as, no, I didn't want to move it here. Anyway, it got moved. Finally, all right. So the Church-Turing thesis, named so because of Alonzo Church and Alan Turing, who essentially became pioneers of the field of computer science as we know it today. And what they're saying is any reasonable model of computation, and the way you can take the modern reading of that is any computational device that you have in front of you. So your laptop, your desktop, even though in practice they might seem very different. My device can't really do, my laptop may not be able to do real-time ray tracing that I need to do using my latest and greatest graphics card in order to play the recent games. But then at the end of the day, Church-Turing thesis is essentially saying that in principle, the ability to compute between all these devices is essentially equivalent. And for sure, the wording here is slightly ambiguous. It's not precise. Even kind of more precise versions of it have some issues with it, but it gives you kind of this interesting kind of initial idea that started off eventually evolved into what one would say becomes a foundational bedrock of computer science, that all hardwares or reasonable hardware. So by reasonable hardwares, we mean, what you would call today universal models of computation. If you're thinking in terms of an engineer, I have the universal set of gates in it, the NAND gate or the not an AND gate, or cellular automata. But if you are not familiar with those kind of theoretical models, just take this idea that I've got a laptop, I've got a desktop, I've got my phone, I've got my tablet, or any other, or my glasses, all of them are equivalent in terms of their computational ability. Whatever I can compute in one model of computation, I can compute in any other model of computation as well, as long as both of them were universal. Now, we won't get too much hung up about the universal bit, but it might even seem something that we may take as a given today, given how prevalent computing is in front of us. But if you were to put yourself in the shoes of a scientist about 100, 110 years ago, where computation hasn't really taken off yet, and people are really building devices specific to particular computations, then it perhaps was not so obvious that, hey, all computational devices in terms of the hardware are equivalent. Whatever you can do in one device, you can do in another device. And as Scott Aronson, one of a pioneering quantum computer scientists, likes to put it, this kind of theorem or really thesis implies as a consequence this lemma of the existence of the software industry. Because what happens because of this thesis is that everyone agrees upon one fundamental hardware of building computers, and now focuses on developing the software, the digital logical code that needs to run on that hardware. So, once you've got that hardware figured out, which you could kind of today agree upon, right? Fundamentally, the von Neumann architecture that you're using to design your laptops versus your desktops is kind of the same thing, right? So Neha, the reasonable model of computation here is referring to essentially a universal model of computation, i.e., your model is not so restricted that you can't even do what one calls universal model of computation. In terms of your basic circuit design, one might think of it as not and AND gates, that if I have access to the not and the AND gate, I can compute any function on it. So that's one way to think about a reasonable model of computation. There are others as well, but perhaps this kind of circuit-based model is the more reasonable way to kind of continue this discussion, given that our quantum computational model that we'll discuss in this workshop is also going to be circuit-based. Right, so, but I would not like people to get stuck on that and just use this intuition that we almost have given our exposure to computational devices, that we never really get in principle stuck on this issue that, hey, if I can run one program on one device, then it cannot be run on another device. For those nerds and geeks among us, you realize that, so there's a popular game, Doom, and there's kind of this popular movement regarding, hey, can I make Doom run on, this old watch or this old portable gaming device or whatnot? The idea behind it being exactly the same, that in principle, one computation can be done on another computational device as well. If I compile my program in C, there is a transformation that can happen that allows me to write and compile the same program in Java as well, or in any other programming language as well. So the logic can be transformed from one programming language to the other. The hardware may be different as well, but as long as I have this ability to translate that code into the native language of the device, one program can be run on any device that I like, right? And so once you kind of appreciate that, then you've got this consequence of existence of a software industry, that I have got one fundamental hardware, and on that hardware, I can run any software that I like. And so the focus of computer science then becomes kind of programming, because in some sense, I've got to figure out what kind of code, what kind of programs can I write, what are the limitations of programs that can I write, and computer engineering kind of becomes a different kind of pursuit in terms of designing the hardware, right? So I know this is perhaps a little bit hand-wavy, but hopefully the key idea gets across, that with the Church-Turing thesis, we are saying that all computational hardware that is sufficiently powerful enough, reasonable, i.e. universal, is equivalent in terms of its computational ability. All right. Whatever I can do in one, I'm able to also do in another model. Yes, there might be a speed trade-off, but in principle, I'm still able to do it. All right, excellent. So with that, there's also a strengthened version of the Church-Turing thesis as well, which is known as the extended Church-Turing thesis. And that says it's not just that any different universal model of computation is equivalent, rather they add in this additional requirement that one model is efficiently equivalent to the other model, i.e. if I write my program in one model, then efficiently, essentially for computer scientists in this case would mean a polynomial overhead. So if I have a program that runs in, let's say, time n squared, where n is the size of my input, then I will have a polynomial overhead in converting that program to run in some other platform. And on that other platform, it will still run in polynomial time. It will not be the case that a polynomial runtime program becomes an exponential runtime program in any other kind of platform or hardware, right? So that's the distinction between what we mean by efficiently simulated on a standard Turing machine. The Turing machine you can think of as a standard computational device. And for a reasonable amount of time, people kind of, and even till today, believe that the extended Church-Turing thesis may be true, that you can interconvert your programs between different programming languages, between different programming models of hardware even, with just a polynomial overhead in kind of transforming the computation from one model to the other. Now, one of the reasons to go into this kind of theoretical background for computer science is that that's exactly what becomes an issue in terms of the argument that quantum computing brings into play, right? So without getting into the initial details of motivations presented by Feynman, kind of what made computer scientists got really interested in quantum computing is this counterexample or potential counterexample that Peter Shor came up with in terms of his algorithm, Shor's algorithm, where he said that, hey, here's a problem, the generic problem of factorization given as input an integer. What are its prime factors? To the best of our knowledge, even till today, we do not have a polynomial time algorithm for doing factorization on a classical computer. However, Peter Shor argued in his paper that, hey, here's an algorithm that if we had a quantum computer, would be able to factorize numbers efficiently, i.e. in polynomial time. So that became kind of a potential counterexample to the extended version of, or the strengthened version of the Church-Turing thesis, because then now you have two distinct computational models, the classical computational model and the quantum computational model, and potentially a problem which is integer factorization, where integer factorization can be done in polynomial time on a quantum computer, but not on a classical computer. And whether or not this actually holds true is still an open question today, because Peter Shor definitely showed that it can be done in polynomial time on a quantum computer. But to this day, we do not know whether or not integer factorization can be done in polynomial time or not on a classical computer. It remains an open problem. Obviously, one of the nice, well, not nice, but interesting consequences of being able to do integer factorization efficiently is that many crypto systems that are used for secrecy in our classical communication networks can be broken. For example, the RSA, the popularly cited example, it's an encryption algorithm used in multiple applications online. You could break RSA if someone had access to a quantum computer, right? So that's, you can see then why computer scientists would kind of stand up and pay attention to quantum computing, because, hey, something really practical and that has been implemented and is used every day. And, you know, if that was 1994, 30 years since, it's now even more practical or more common, using online banking, using doing transactions online. The fact that you could break RSA has much larger appeal and consequences. And so people definitely are more interested. Having said that, an initial motivation for quantum computing is just as much, if not more, practical and of consequence, even though perhaps initially computer scientists didn't think about it in that way. And that's what was Feynman's initial motivation, that, hey, if you want to simulate quantum physics, then you want to simulate it on a quantum computer rather than on a classical computer, because then that simulation would be efficient. And I'll say more about it towards perhaps the later part of the session tomorrow or early tomorrow. Right? Did I miss any specific question about this? So hopefully not. If not, you can always post your question again in the general question section, and I'll try to get to it later. Okay, so that's kind of the brief, very, very brief, very limited kind of motivation for where we are coming from in terms of why people from computer science got interested in quantum computing. That, hey, there's stuff that can be done on a quantum computer that at the moment we don't know how to do on a classical computer. Then let's try to really understand the limitations and the boundaries of this new situation. What is it that we can actually do on a quantum computer that is not possible on a classical computer? And what are the consequences of that? And that has had great dividends, right? So for example, the reverse has also happened, that people came up with a quantum algorithm that initially seemed like not possible on a classical computer, but then it was shown that, hey, you could dequantize the quantum algorithm and make it classical, such that you got a new classical algorithm for solving a problem efficiently that we didn't have originally. But the idea for how to solve that problem efficiently on a classical computer actually emerged from an efficient quantum algorithm. So there's really interesting stuff like that. So sure, so perhaps to clarify some of this discussion. So yes, Peter Shor's algorithm is known for sure to run on polynomial time on a quantum computer. It can't run on a classical computer. You can only run a simulation of Shor's algorithm on a classical computer. So going back to your Church-Turing thesis, this becomes this issue in terms of the extended Church-Turing thesis. If I had a quantum computer, then I don't need to simulate quantum computing, right? I just run the quantum algorithm, which is Shor's algorithm, on my quantum computer, and I solve integer factorization in polynomial time. But now, as we are in a current situation today, I'm running it on a classical computer, so I have to simulate quantum computers on a classical computer. We don't know how to do that efficiently. So our best possible simulation of Shor's algorithm on a classical computer takes exponential time. And so that becomes kind of this exponential separation between classical and quantum computing, and that falsifies the extended version of the Church-Turing thesis, potentially. Why potentially? Because we do not know, or we don't have a proof that factorization cannot be done efficiently on a classical computer, right? So there's this subtle distinction that's important. Can quantum model be realized in a Turing machine, right? So it's nice to expand this question a bit in terms of what we've been discussing about. So for sure, we can simulate quantum physics on classical computers, if you want to call them classical Turing machines. But the insight that Richard Feynman had in the 1980s, among other scientists as well, approximately at the same time, is that any simulation of a quantum system on a classical Turing machine on a classical computer seems to be inherently running into a limitation in terms of having an exponential runtime requirement. Why is that? I'll try to kind of give you a good motivation, hopefully by the end of this session today. So in principle, yes, it is possible. So we are not violating the original version of Church-Turing thesis. So for sure, classical computers can simulate quantum computers. There's a general understanding that everyone agrees upon, even though if you are going to look at fringe literature, there's still some papers out there that would say, hey, quantum computers can be used to do something that's not at all even possible on a classical computer. For the large part, I think those papers either are discredited, have an issue with them, or whatnot. So most of the active computer science community believes and understands that classical and quantum computational models are equivalent in terms of the Church-Turing thesis. What is at issue, and is an open question, is whether or not they are equivalent in terms of the efficiency. So integer factorization is known to be doable in polynomial time on a quantum computer, but we do not know whether it can be done efficiently on a classical computer. And that's the open bit. If tomorrow someone proves classical computers can factorize integers efficiently, then this example or potential counter example from Shor's algorithm kind of goes away, because you would have an example now, or you would have a situation where this problem for integer factorization has polynomial runtime on both classical or quantum computers. Having said that, it's not as if all practical applications of quantum computing go away, because you still kind of go back and say, well, what was the original motivation presented by Feynman? Well, that was to simulate quantum systems, and that's still going to be an open question, whether or not quantum systems can be simulated efficiently on a classical computer. And hopefully by the end of the day tomorrow, I'll have given you a bit more technical understanding and motivation of how to think about this question.
We will have a little break now, and then we will enter the second part of this session, namely the QBronze second lecture with Jibran. But I would like to take the opportunity now to also introduce one more team member, Jasmine, who has been answering lots and lots of your questions on Discord. We just added your spotlight, Jasmine. Would you like to introduce yourself to everyone?
Oh, hello. So I am Jasmine. I did the Womanium quantum program last summer and really enjoyed it. And I was very excited to come on as a volunteer and help them do more of that in the future. So here I am again, messaging all of you like mad. You are wonderful souls, so we will get all of this resolved. But yes, my background as far as quantum, I got into it in high school. Towards the later part, I knew I loved computer science at that point, and I loved physics and AP physics. And then I heard about quantum computing from a sci-fi teen novel, and I thought it was like, oh, this is a plot device to keep the book moving, right? Like that's kind of too cool to be real. So I Googled it. It's like, no, it is real theoretically. And I thought that was amazing. So I looked into it more and I loved it. And as I went through college after that, I took any chance I could to study and learn about it more through books and courses or classes at my college. And now I'm a software engineer by trade and a quantum enthusiast, hobbyist by passion. So that's what I do.
Amazing. And Mohammed Ali from Iran says Jasmine is a perfect team member. I agree. This is a good question from Mohammed Ali, quantum computing for bioinformatics. We will have a lot about quantum applications also in the upcoming weeks. So definitely keep this in mind while you start exploring quantum algorithms yourself, how it could be useful to your field or to other fields that you find interesting. I see some people raise their hands on Zoom. Please ask your question on Discord. The link to join Discord is in your welcome email. That one has been sent from the quantum@womanium.org account. If you only signed up maybe on Sunday or yesterday, you might not have received that email yet, and it will come tomorrow or within 2 days. Rafael from Ghana asks, should we start learning about quantum computing on the Canvas website? Canvas is one of our main learning platforms. So we have Zoom for the live lectures, plus a YouTube live stream. Then we have Discord for all communication, announcements, discussion. And Canvas is where you find all the exercises, links to the lectures, and also more guidance on how to walk through this program. This is how you should see it. The most important tabs are Home and Modules. If you go to the home page, you see an overview of the modules. And for the modules that we are currently doing, you see the qualifications needed to earn a certificate. Modules is the main part. Just start from the top, from getting started. There you fill out more about yourself in the pre-program survey. You do the pre-program quantum level assessment. Please do this with your current status of knowledge. So it doesn't matter if you score low, for example. We just hope that in the end quantum level assessment after the program, you score higher. So we see that you made progress this summer. And then here in Get Started Launch Session, we just added the slides from yesterday and also the recording from yesterday. So you see that here from top to bottom, you can walk through 2 optional modules. You can play the Quantum Odyssey game here. We will have a demo tomorrow, and you can prepare yourself better, learn more about quantum mechanics, and learn more about the quantum computing basics. And these are both 1 lecture and then a short quiz for yourself to learn better. And then you get to the QBronze module, which we have started yesterday. You can do the installation, as in this very first guidance. If you already did it, you can upload your previous certificate here, and then you don't need to do the other quizzes anymore. You can do them if you want, but you don't need to. And then you will see some quizzes here, 1.1 through 1.5. There will be 1 or 2 quizzes after each lecture, and they help you in your learning. Additionally, if you score at least 50% in each quiz, that is 10 points in each of these, and 70% overall, 70 points overall in this module, you will earn the certificate. There are also some more exercises to help you in Jupyter notebooks. And all that guidance is here in this Get Started quiz. You see the link here to GitLab, and from there you can get started and download these exercises that are available for every lecture, and you can use them as much as you want for your own learning.
Excellent. All right, time to get started. Thank you very much, Marlou, for the wonderful introduction again. And hopefully today we'll be able to jump right into all the fun stuff. And I think many of the technical questions that were coming in during Olivia's session as well, hopefully some of them I'll be able to answer for you with kind of some technical details today. And for sure, some of them we'll be able to get to tomorrow. I see someone asking for Jibran's LinkedIn profile. Unfortunately, Jibran doesn't have a LinkedIn profile. So yeah, apologies. Anyhow, all right. So as I mentioned yesterday, to kind of connect back to where we left off, the QBronze workshop is kind of presenting quantum computing from a computer science perspective. So many of the questions you might have about quantum mechanics and quantum computing that come in from a physics perspective in terms of, hey, what's the underlying physical process or whatnot, those details might be abstracted away, not to say that they're not important. For sure, they are even of more fundamental importance. But with the computer science approach, we are focusing on the algorithmic perspective, right? So we want to be able to identify, assuming the rule book of quantum mechanics, what can be done through a quantum computer. So that's essentially kind of the key goal from the computer science perspective, right? So we take quantum mechanics as a given, and the physicists give us kind of the rule book for quantum mechanics, pretty much like how we have the rule booklets of classical mechanics. And then what we want to know and what we want to do is, hey, what can we do with this rule book of quantum mechanics when we build a quantum computer? So towards that end, the first kind of part of the session today will identify how we really think about computation when we build it for classical computers. And then we'll transform that language to computation about quantum computing. And hopefully you'll be able to really see the nice technical connection between the two and how the mathematical machinery really just needs to be fine-tuned in a couple of places for us to go from classical computation to quantum computation. And so it's really insightful in the sense that we get a better understanding of what's the key distinction between these two perspectives. So towards that end now, so let's say we've got a physical system, and I want to abstract away from all the physical details of that system, apart from the fact that, let's say I want to be able to identify, hey, how many unique states can that system be in, right? And so from a classical computer science perspective, obviously what you're trying to get at is, hey, I'm thinking about representing two unique levels of a system or two unique states, which we identify as a classical bits. It does not need to be a bit as well, right? So anyone who starts off computer science, was interested in computer science early on, has at some point a question, hey, why do we build classical computers using only classical bits? Why not have a 3-level system or a 4-level system? We'll get towards that in slightly as well. But to begin with, what we are saying is, hey, if we have a physical device, we don't worry about the physical details. Is it a photon? Is it an electron? Is it some other kind of physical system? For now, we don't care. All that we care about is, hey, it allows us to represent or identify some unique finite number. Everything that we will pretty much do in this workshop will be about finite stuff. And obviously, it should be non-empty because we should have some stuff in there, set of states. And so now there's nothing special about what are the symbols you associate with those set of states, right? So the usual language that a computer scientist might use is to say, I have an alphabet. So this unique set of states, a computer scientist would call them as an alphabet, that these are the symbols, the unique primitive symbols that I will work with. So in the bit binary case, I would say, hey, I've got a 2-level system and I identify them as, excuse me, zeros and ones. So a single 0 symbol and a single symbol for 1, but there's nothing special about them. I could have a happy face and a frowny face. Obviously harder to draw, but that works as 2 symbols as well. So all that I'm identifying to begin with is that I have a physical system that can be in some number of states. And I have a unique symbol associated with each of those states. So for example, I could literally have A, B, C, D as well, alpha, gamma, delta, or whatever. So moving forward, pretty much we'll fix our alphabet to be 0, 1, the set of states to be 0, 1. Right? So this is essentially then us linking the motivation kind of for doing this abstraction then is we're figuring out how to represent information using this physical system X, right? And as soon as I've represented information or stored information in this physical system, the very next thing I would be interested in is transforming that information or doing some computation on that information, right? So one simple way to think about computation on a single bit is just this kind of Boolean function. So I'm thinking about a function, it's Boolean if it takes as input a single bit and it outputs a single bit as well, right? So just based on this notation, how many functions do you think exist that map a single bit to a single bit? How many unique mappings can I have of this form? Kind of the table already hopefully gives it away. Excellent. So I've got 2 and a 4. So 4 again, 4, excellent. 4 is 4 wins by majority. 2 perhaps is the answer because people are disregarding the trivial classical cases where you've got constants. So, right, so the way we can fill in this table, imagine I've got my single bit represented here by small x. It has 2 possible values, 0, 1. And now each of the column headings over here are identifying the 4 unique functions I can have for that single bit. And obviously we can verify that these will then take the form. Well, I could have the constant function that always outputs 0. I could have the identity function. I could have the negation function. And I could have the constant always output 1 function. Right? So these are my 4 functions that exist for mapping a single bit to a single bit. And so for people who answer 2, perhaps you were thinking, well, these are trivial, always output 0, always output 1. So these are kind of the 2 interesting functions. Even between them, one is just the identity. So the really non-trivial computation that we're doing is this negation or flip by this function, right? So nice. So that means we, in some sense, encapsulated deterministic computation over a single bit, right? Now, how would we generalize that? Well, to begin with, easy computation that I'm sure all of us have at some point thought about. If I've got n bits, Shamrita is already kind of answering a question that I didn't even ask. If I have n bits, how many different possibilities are there? There are 2 to the n possibilities. Excellent, right? So for example, if I have 2 devices, let's say x1 and x2, the way I might represent them is by saying, hey, rather than just a sigma, I have something called sigma 2, and that will be all the 4 possibilities. Note now, I'm not representing the 4, I'm not representing the functions anymore now. I'm still going back to representing the unique set of states I could have if I had 2 physical devices, each of them taking 2 possible values, right? So I just write down the 4 possible binary strings that exist of length 2. And as people are already familiar over here in the chat, sigma n, that would represent or would have size 2 to the n number of possibilities, right? So if I have n physical systems, each of them having 2 possible values, simple counting argument, 1 bucket, 2 bucket, 3 buckets, n buckets, each of them have 2 possible values. I multiply them out together to get 2 to the n number of possibilities, right? So if I have n bits or n physical systems that can take 2 possible values, then I have 2 to the n different possibilities. I can represent 2 to the n different unique states in some sense. Now, how about we connect it to the second part of what we did earlier? What about the number of possible functions I could have over this n bits? Right, so we've got 2 to the n possibilities for different possible states of n bits. But now if I wanted to do a computation over these n bits, what about a function that will now map these n bits? And for simplicity's sake, I'm not mapping it to n bits now, like we did in the previous case. I'm thinking of it as just a Boolean function, which in this case now is mapping n bits as input to a single output bit, which just takes a value 0, 1. So I assume the first answer is n. With it is saying 2 to the n. Arshit is saying same as before. So you don't need to send a direct message in Zoom chat. You could send it for everyone. When Arshit was saying same as before, I'm not sure what the before answer was here. But now, so for sure there should be a dependency on n, right? I'm asking about n bits as input, so the number of possibilities should depend on n. Most of the answers are of the form 2 to the n. There was one answer that was 2 to the n, 4n. Can't get the question. So the question is, in the previous case of just a single bit, we identified that there are 4 unique functions that map a single bit to a single bit. Now we identified that if I have n possible bits, how many different mappings will exist, unique mappings that map n possible bits as input to a single bit as output? How many such computations, how many such functions exist? 2 to the power n plus 1, 2 to the n, right? So there's a bit more variation now in the different answers that we're getting. And we can easily kind of verify quickly that if you apply the same reasoning as before, you get an answer that looks similar as before, but it's not the same. So what do we do? Well, what are the number of different possible inputs I can have now? Well, I know already it's 2 to the n. Well, I can write them down in a table where the 2 to the n values go from all 0 string to the all 1 string. I've already verified that this will be 2 to the n number of possibilities. So this table has 2 to the n different rows. Now, if I want to fix my function, this function will actually be fixing this entire column, right? So if I fix this entire column with 0, 1 entries, then I've fixed one particular function. Agreed? Right, so if I say, hey, here's 0, here's 0, here's 1, here's 1, and so on and so forth, for all the 2 to the n possibilities in the rows, then I have fixed one particular function, the kind of Boolean function that I'm interested in. Agreed? So people are still giving the answer, but like everyone, okay, yeah, all right, good. Agreed. So now there are 2 to the, just like there were n buckets over here, there are 2 to the n number of buckets or 2 to the n number of rows in here. So this bucket has 2 possibilities, this bucket has 2 possibilities, and so on and so forth. So it's 2 times 2 times 2 all the way till the bottom row, last row. So I get 2 to the 2 to the small n. So what's very nice and interesting over here, it's not just 2 to the 2 times n, but it's rather kind of a super exponential. So it's 2 to the 2 to the n. And so that's kind of very nice, right? That so no, 2 to the 2 to the n is not the same as 2 to the n. Yeah, if you can make it capital N, then that's fine. If you make 2 to the small n equal to capital N, then for sure you can write this as 2 to the capital N. So what's to take away here? It's interesting that the space of functions or space of computations that could exist for information or input size of size 2 to the n is again kind of exponentially increasing. It's 2 to the 2 to the n. And so in terms of looking for different algorithms, looking for different kind of machine learning classification classifiers as well, we identified this now that this really is going to be a really, really hard problem, because if you've got n possible inputs to begin with, the number of different possibilities are not just exponentially large, they're super exponentially large. And so this really is a difficult problem in terms of figuring out, hey, what's a nice algorithm that maps this input to this output? What is a nice classifier to learn a certain classifier for kind of input? So both machine learning, algorithm design are doing kind of stuff that's really, really difficult. Sure. So very quickly, we identify that in order to fix a Boolean function that maps n possible bits to a single output bit, what I'll need to do is to fix this entire column of entries to a single 0 or 1 for each row. Very much kind of like how I figured out, well, how do I identify the n different possibilities for n bits? Here I'm identifying what are the 2 to the n different possibilities for each entry in this row. So I probably stepped away from my device, so hopefully the voice is clearer now. Let me know if it's still not clear. So what I'm doing is I'm trying to fix each single bit in this row, and there are 2 to the n possible rows, right? And each bit has 2 possible values. So it's 2 times 2 times 2. How many times? It's 2 to the n number of times. And so that's why I get 2 to the small n or 2 to the capital N. So just to kind of take away from this, again, that the number of possible computations. So think of F as a computation we would be interested in. The number of computations you could do, numbers of algorithms that you can design really blows up. And so, you know, we already get kind of an idea that thinking about computation, thinking about maps, in where we're interested in here, how does this information map to just a yes or no answer? The answer that we were interested in over here was not a complicated answer, right? We were just saying, hey, for each input, give me an output which is just a yes or no. And even though that might seem limiting, most problems can be reduced to such a decision problem. So computer scientists usually love to work on problems that they call decision problems. And it's possible to really map nearly all problems to this structure, which initially might not be obvious, because you're like, hey, my problem is an optimization problem, which has an optimal value of 3.274 or, you know, 191.2 or whatever. How does that map to a single decision 0 or 1? And hopefully, as we go along, that will become clear in terms of how we can do that mapping. Good. So in some sense, if we have got perfect information about my physical system, so let's kind of quickly put on our like pseudo physicist cap, and like, if we had perfect information, perfect knowledge about my physical system, then in terms of characterizing the kind of computations I could do with it, in some sense, this slide kind of packages it up nicely. There's no error, there's no probability, there's no noise. And so I have clearly figured out, well, what, at least in terms of counting, how many different possible computations can exist and what's my amount of information. However, obviously, the real world is not so simple. It's not going to be deterministic, perhaps. I won't have complete information. And so we are interested in, what if I have incomplete information about the physical system that I'm working with, right? And so when I have incomplete information about the system I'm working with, what's a commonly used mathematical tool that we bring in? We already referred to it last time. I already mentioned it as well. What's kind of a nice mathematical tool that we use to model uncertainty or incomplete information about any kind of piece of system or, yeah, excellent, probability, right? So that's exactly what comes into play. So I will use probability to represent the fact, and through probability I get statistics, yeah. I will use probability to represent my lack of information or knowledge about this physical system. So I don't know, so, you know, I flipped a coin, I don't know the bias of the coin, it would be some probability P, so I know with some probability P it comes up head, and 1 minus P comes up tails, and so the nice little world of 0 and 1 is replaced now by kind of this number between 0 and 1, right? So if I flip a coin, or if I have a physical device, it's not just a coin, and I'm not sure whether that physical device is in the state 0 or is in the state 1, I can only associate some level of certainty or some level of probability with it. So I'll get some thing of the form where I'll say, hey, the best thing I can say is that the probability with which the state of the system X is 0 is, let's say, probability P. And if it's a two-level system, then automatically for the system to be in state 1, the probability becomes 1 minus P. So I've got kind of these two numbers. For sure, just the parameter P is enough. But it's nice to represent them together as a vector as well, right? So we usually would take this P and 1 minus P and write them out together, maybe even give them its own name. Hey, this is a vector, maybe with a hat on it, or whatever notation you prefer for probabilities or vectors. And implicitly, we've got kind of an index of this vector as well, right? That this P represents, let's say, the physical system to be in state 0, and this for the physical system to be in state 1, or that the state of the coin was head, or the state of the coin was tails, or whatever else alphabet that I was using to represent the two unique states, right? So yeah, we are getting started with probability in this case, in this session, but we will end up with identifying the corresponding mathematical structure for quantum computing as well. But the initial part, definitely Mohammed is going to go classical probability and operators. Alrighty. Now, one kind of nice thing to note over here, and just make a mental note of this, we'll come back to it when we come to kind of quantum systems and representing quantum information. That is, whenever we look, you know, you won't give a second thought about looking at a classical coin flip, apart from, well, realizing what the result of the coin flip was. So let's say if I flipped a coin, and now I look at that physical device X, right, which could have been a coin, or could have been something else, you know, the light switch that I used or whatever. Whenever I'm looking at this coin or this switch, I will not actually see the vector V. I will not even see the probability P, and obviously also not 1 minus P. And it almost might seem like a trivial thing for me to state over here. That obviously all that I will see is what? I will see exactly the labels in some sense that associate with the states of that system. Right, so somehow I could be able to say that if the states of the system, again, we go back to those deterministic symbols that we had identified from that alphabet, I will just see or observe the state symbol with the corresponding probability V sub sigma, right? So in this case, let's say I will see heads with probability V sub H, let's say, which is P, and V sub T, which would be 1 minus P. So the operational or empirical output of a probabilistic observation of this probabilistic system is not going to be either the vector V itself or the probability P, but rather just one of the symbols that we associated with the system. And we'll see that that's something that obviously happens in the quantum case as well, but sometimes can lead to a little bit of confusion, which we'll get to. Multi-level systems, we're about to get to that, Nela, soon, right? So how we represent, so you're asking multi-level, not multi-party. A multi-level would be, let's say, good. So if I had a 3-level system, right? So I could have x equal to 0, x equal to 1, and x equal to 2. Well, then I could say, hey, this has probability P1, this has probability P2, and then because of normalization, obviously, this would be 1 minus P1 minus P2. right? So you'll have a bunch of probabilities, and essentially what you'll identify is that the entire vector has to be a probability vector, right? And you can generalize this to any dimension n. I shouldn't use n because I already used that for the number of bits. All right, any questions here? All right. So obviously then, how do we transform this information? Just like we were looking at transforming classical information when it was deterministic. Well, let's quickly see an example. If I had this vector p1 minus p, given that we know matrix algebra, then we already are familiar with that. Here, there's something called matrix vector multiplication. So I could take this vector p and 1 minus p and multiply it with matrices to get new vectors. How do we calculate these probabilities in classical systems? Excuse me. So I assume right now that we are told, or we are able to identify what these probabilities are. Some examples in the Jupyter notebooks will lead you to exercises where we actually exactly gain statistical information about how confident we are, what are the probabilities. But for now, let's just say we know what the probabilities are for the specific questions that we're doing. Now, going back to just this quick example that we're doing, just to get an idea of how do we do transformations for classical information, which is incomplete, i.e. we are interested in how we map vectors to vectors. Well, we will multiply them with matrices. One possible matrix, for example, could have been 0, 1, 1, 0. Very quickly, what would be the output in this case? If I were to multiply this matrix with the vector p1 minus p, hash note. All right, so very quickly. So Akash asked a quick explanation again of the note. So very briefly, the observation that we are just making, a trivial observation in some sense, that when I look at the coin that I just flipped, so let's say the physical system X that I was interested in was a coin. I flipped it. Obviously, when I flip a coin, I don't see the probability P, right? I don't see the vector V as well. The vector V is really a mathematical construction that we have to represent information about this object. All that we see are, again, the state symbols that we had associated with heads and tails. Right? So I would say, hey, the coin came up heads, or the coin came up tails, the switch is on or the switch is off. So whatever were the symbols we associated with those two kind of different unique states, that's the output, right? No, this is for classical systems, right? We haven't started anything about quantum yet, but we'll see there will be something very similar happening there as well, obviously. And now going to the example, people already shouting out in the chat that obviously this will be 1 minus pp. And in some sense, you verified that this is the negation operation that we already see in the deterministic case. This is that same operation now represented as a matrix. Now, a very nice kind of thing to kind of link also is, well, how do I think about these 4 entries in terms of what they are doing? I already kind of verified this explicit example, but then you kind of already see what's happening in this case. So had these 2 entries been 1, 1, and the anti-diagonal entries been 0, 0, then this would have been the identity matrix, right? So in this case, this matrix signifies an operation that we are doing on the physical system, just like the Boolean functions f was signifying a deterministic operation that we're doing. In this case, this again still is a deterministic operation that we do on the system, right? Which leads us to, well, what are the 4 possible deterministic operations represented as matrices? Let's quickly write them out. So the 4 deterministic operations that we had identified previously on classical bits represented as matrices could be written down as, let's say, always output 0, always output 1, identity, and the one that we just verified in the previous slide, negation. Right? So the 4 Boolean functions that we identified, Tego, where did I lose you? matrix or all matrices. Right. So in this case, these four matrices are the deterministic matrices that represent the four Boolean functions that we identified in the first slide for the deterministic Boolean functions, right? So these four Boolean functions that were mapping a single bit to a single bit, we can verify that these four matrices perform exactly that transformation, but now over kind of probability vectors rather than just a single bit as input. So I get my ability to transform deterministically my probability vectors into other probability vectors, right? So I see some messages where people kind of are finding it hard to follow along. So perhaps one of the key things that's happening over here is that I'm assuming people can follow the matrix algebra in terms of just multiplying out matrices with vectors. If that's the case, I strongly recommend using a matrix algebra reference. The Jupyter notebooks already do have a brief background in kind of matrices and vectors. So you definitely want to review those in order to follow what will happen for kind of pretty much most of the session moving forward. And that's really the key thing to observe, right? That all of this is really just talking about transformations, Boolean transformations represented in terms of matrix algebra. Right? We haven't done anything quantum yet. All that we are talking about is classical transformations on classical information. Right? Right, and so a good exercise for you after you work through it is to identify why these four vectors, these four matrices correspond to the four Boolean functions that we identified first. All right. Okay, but as one might argue, so apologies, I just assume that people have some matrix algebra background. I realize some of the people right now on Zoom don't have it, so please follow along via the Jupyter notebooks first, and then hopefully if you come back to the recorded video for this, it would make sense. But unfortunately, I won't be able to go back and do all of matrix algebra here as well. Alrighty. A1 and A2 are same, and A0, A1. No, A0 and A1 are not the same, right? So a quick way to verify it is basically just multiplying out these matrices with specific probability vectors and see that they are not the same. In one case, this is always output 0, and let's say this is always output 1, assuming you make the corresponding indices, this being 0, and let's say this being 1, and vice versa. All right, so why did I select these four? These four are just, these four matrices are the matrix version of the four Boolean functions that we had identified in the first slide. However, you can definitely think about what would be the probabilistic version of these transformations. Obviously, there will be more, right? They won't be just these four transformations. Just like in the classical case, I had 0 and 1. That was deterministic information. However, when you do probabilistic transformations, you're allowed to take a mixture of, let's say, these four deterministic transformations. And so in this case, to get a probabilistic operation, right, you can say, hey, I will take a weighted combination of these four matrices. And these matrices indices run from 0 to 3, right? So this is me saying really just P0, A0, plus P1, A1, plus P2, A2, and P3, A3. Now, the P over here is not the probability that we had previously for the two-level system. Rather, the P over here is representing the probability with which the gate, if you prefer to call it, or the matrix or the transformation A0 is applied. P1 is the probability with which A1 is applied, and so on and so forth. So operationally, automatically, it kind of makes sense to think about this, that if each one of these four matrices were deterministic transformations, then the probabilistic combination of these four transformations is also going to be a valid classical transformation. All right. So yeah, these slides over here will be posted, so don't worry about that. The link will be posted on Discord. So for example, let's quickly verify that if I were to choose just half A2 and half A3, what would be the corresponding transformation that I would get? What's the new resulting matrix? So right now, we don't have to worry about calculating eigenvalues or eigenvectors. So these half are the probabilities, right? And so I fixed P0 and P1 to be 0, P2 and P3 to be half to get this kind of combination over here. And so what would be with this combination? You will get, very good, we're getting the answers. It's just basically, so you see the matrices now end up looking a bit more interesting than just 1, 0 entries. And so the entries are, in fact, as we'll quickly see, each entry in these matrices can be thought of as a probability itself, right? It will represent the transition probability if my state is in, let's say, whatever is the index of the column to transition to whatever is the index of, let's say, this row or this row, all right? In fact, this matrix, in some sense, you could also think of it as, let's say, a classical coin flip, where the bias is exactly half, right? So if you apply F to any matrix P1 minus P, what comes out? Right, so all half entries, very good. Many people give the right answer. Now, what about applying F to just the probability vector P1 minus P? It's the next state of the system, but now in this case, what is the next state of the system? So if you just do the matrix vector multiplication, you'll verify that this just gives us half 1, 1. And that's kind of the reasoning for calling it the coin flip kind of matrix, right? Because no matter what the input system was, no matter with what probability I started with a head or a tail, let's say, the output is always going to be a coin, a head or a tail with probability half each. So it's like simulating a perfect coin flip with no bias, right? So it's exactly a fair coin flip, right? So we've seen how to take deterministic transformations and through them build probabilistic transformations, but there's a nicer way to characterize the space of transformation as well, which we'll try to build up to. But before doing that, let's kind of do one more example that perhaps motivates why kind of doing all this mathematical machinery has some payoff, has some benefit, right? So let's take this slightly more interesting, non-trivial protocol. So this is kind of a two-level operation. So we assume we have got a coin, and that coin, we a priori don't know what's the probability of it to be head and tails. And I'm assuming in this case that the first index is referring to the tails, and the second index is referring to the coin being head. So I've got a coin which will, when flipped, come up tails with probability P, and will come up heads with probability Q. So that's kind of the result of the first coin flip, if you flip this specific coin. Now, the protocol that I will follow is that after flipping the coin first once, I will flip it again, and I will follow these rules for whether or not I'm flipping it again. If the result of the first coin flip is a head, I will flip the coin again. All right, so I flipped the coin once. With probability P, it came up tails, and probability Q, it came up heads. And now I observe that if it indeed did come up head in this first coin flip, then I will just flip the coin again. And in the second case, if we get a tail, then actually I will not flip the coin, but rather just deterministically kind of turn it over such that the coin's state becomes a head, right? So there's kind of this two-level procedure that I'm implementing. For sure, you could individually work out the probabilities of, well, how this protocol gives you heads, tails, heads, or whatnot. But we'd like to kind of nicely characterize this entire protocol, let's say, as one single transformation. And so what we'd like to think of is, can I characterize this transformation, this protocol, as kind of this probabilistic operation that we thought of in the last time. So let's say as kind of as our convention over here, that the first index is for tails, the second index is for heads. Similarly for the row, the first index is for tails, the second index is for head. And now again, we'll reiterate the convention that this tail versus, let's say, this heads. What's the understanding of the entry that goes in this index? Well, it corresponds to exactly the probability with which, if my system is currently in the state tails, what's the probability with which it will transition to state head? All right. So let's kind of make a note of this. So this, and then given this entry over here is given that my current state is tails, given by here, this entry gives the probability to transition to heads. Why? Because that's the index of the row over here. Alrighty. So now let's just work through it. We got some people are asking about Hadamard's. Kind of give me kind of till the end of the session. We'll get to Hadamard's as well, whether or not this is like applying Hadamard from the previous case. Alrighty. So what I'd like to do now is to take this protocol over here that's listed here and use it to fill in this matrix over here. I see some of the people have already shouted out answers. That's great. Not all of them necessarily correct. So for sure, let's say let's take the simpler case, right? So if we get a tail, so I know that I fixed this column, then the coin, we just deterministically flip over to make it a head. So in this case, for sure, the new state is a head. So this will be a 1 and this will be 0. Now note the way I have identified the meaning of this transition over here automatically gives us this intuition that each column in this matrix can now itself be thought of as a probability vector. And that's a very nice intuition to have, right? Each column of this matrix, if this is really going to be a valid classical transformation, is really going to be a probability vector in of itself. Because this column over here identified exactly what we do in this specific situation, which itself identifies a probabilistic process. Similarly, over here, if we get a head, we flip again. Well, if we are flipping again this coin, what's the probability it comes up head? What's the probability it comes up tails? And so that's where perhaps some of the participants got confused. In that case, note, we did not say that we have a fair coin. So it won't necessarily come up half-half. It will come up tails with probability P, and it will come up heads with probability Q. Right? So that's why these entries over here will be P and Q. So apologies if you got confused just from the previous example where we looked at F as this half-half, all half entry matrix. But here, this is not the F matrix that we're making. It's really just this other transformation corresponding to the protocol that we have over here. Right? Hopefully it makes sense. Some people, yes, already saying it makes sense. Good. Hopefully it also clear why the second column is not half-half. Alrighty, so what's the big payoff? Well, if we did this, now figuring out the new probabilities of, well, what's the probability with which after this protocol is done, the coin is in state heads or state tails, I really just need to do this matrix vector multiplication to get a new vector out, which I'll let you verify, ends up being PQ and P plus Q square. So totally not kind of trivial or obvious probabilities to begin with, right? Excuse me. Right, so you've got these two different probabilities, but they precisely identify with what probability will the state of the system be head or state of the system be tails after performing these transformations. So not the new matrix, but the new probability vector is this vector. And this, again, connects us to a nice way of thinking about these classical transformations. It's that all matrices will represent valid classical transformations that will map probability vectors to probability vectors, right? Because the output after the transformation has to be a probability vector as well in order to make sense, right? And the only way that will happen is if the columns of each of these matrices are probability vectors as well. So yeah, sure. So I'll repeat. The way to think about these transformations, what is the space of classical transformations? It's the set of matrices that will map probability vectors to probability vectors. Well, obviously, because if the output is not a probability vector, then it's not really, representing probabilistic information the way we defined it to begin with. We said that, if you've got probabilistic information, then the way to represent it is via probability vector. So if I apply a gate, if I apply a transformation, if I do some kind of information processing protocol, and I'm keeping all the information in some sense contained, right? So there's no loss of information to the environment kind of thingy. So then all of this information is still contained in my vector. So that means the classical matrix has to transform a probability vector to another probability vector, and that gives rise to a nice characterizations for which we can say in general, any matrix is a valid classical transformation if two things are satisfied, which is essentially really just one thing. Requirement 1, all the entries in the matrix are greater than or equal to 0. And 2, sum of entries in a column is 1. In other words, they have a nice name for these kind of matrices. You call all these matrices stochastic matrices. There's much more to it. There are exercises for it in your Jupyter notebooks that you can work through to get kind of more intuition about them. But you note now how this corresponds to exactly the intuition that we had given this labeling, that what we end up having if we satisfy these two requirements is that each column is really just a probability vector. Can I explain the head column again? I'm not sure which part of the head column you're referring to, Yashasvi. Right. To get the probability, is there such a thing as negative probability? There are a bunch of nice kind of exploratory papers that look at negative probability. For our purpose, we won't kind of work with negative probability, but for sure we'll perhaps take just as good a version in terms of talking about quantum amplitudes. We'll be getting to them soon, hopefully. The column part, how we put P and Q. Right, so quick verification of why we have P and Q over here, because the protocol said if we get ahead, so we know we have fixed our column label to be ahead, we will flip the coin again. Now, flipping the coin again, what's the probability of getting a head and a tail of a single coin flip? Well, that was given as this first piece of information, right? So this is a coin that whenever we flip it once, the probability we come up tails is P, and the probability we come up heads is Q. So we really just need to plug in that vector over here in here, right? Right. So Mohammed, so these are two individual probability vectors, right? So when you say it's a four-membered vector, sure, yeah. So there are cases when you can think of vectorizing this matrix as a vector, but we don't necessarily need to get into that right now. But yeah, it makes sense to think about it that way if you want to. All right. Okay, so for sure, this might be too much if you aren't familiar with matrix vector stuff. So hopefully you can kind of come back to it later as well. Where the recordings, post your questions on Discord, and hopefully we can do that as well. So I'll try to move on, and then if there are still questions about this particular slide, I can take them on Discord. You can post them in the QBronze program module session in Discord. Alrighty. as someone asked about higher levels, well, let's go the other way around, like we did for deterministic systems. What if I have more kind of physical devices, but each of those devices are devices regarding which I have incomplete information, right? So I could have coin x1 and I could coin x2. And both of them may actually follow a different probability vector, right? So this one might be PQ, this one might be RS. How do I combine these two probability vectors? Here's something that probably very few of you might have seen, but it's doing something that intuitively you've always been doing when you got introduced to probability and doing sample spaces and calculation of probabilities in sample spaces. That's all that we are doing here, Nigar. So all that we are doing is calculating the probabilities of the next state of the classical system. Awesome. Alrighty. So how do I combine the joint information of these two coins, or these two physical systems? Well, we do something called a tensor product. You take the first vector, you write down this x inside a circle to represent a tensor product. You write down this vector, and now the way you combine it is really you take just all the possible combinations. So you get PR, you get PS, you get QR, and you get QS. Well, why these four numbers and why this ordering? So think about it this way. If this was tails, this was head, this was tails, this was head, and when I'm combining these two different physical coins being flipped, and I want to look at the sample space of the events that will happen, well, it could be, well, what's the probability the first coin came up heads and the second coin came up tails, and vice versa, or both of them came up tails, both of them came up heads. There are four possibilities, right? Exactly using the same kind of counting argument that we've seen previously. So the way you could think about these four probabilities in this vector are, and indeed these will be probabilities because these are just probabilities being multiplied out together. And the index of this, excuse me, vector could be thought of as being labeled as tails, 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 heads, heads, tails, head, head. So all that we've done via this tensor product is combined the four different probabilities of the bigger sample space and written them down in my probability vector, right? And note how the dimension of this vector has increased. If initially these two initial vectors were of size 2, then the new vector is of size 4, of dimension 4. Now, if I had n such vectors, the dimension of the vector, the resulting vector, will be 2 to the n, right? So here's a nice kind of, again, mental note. This increase in the number of possibilities of the vector to be exponential is something that's already happening for classical probability vectors as well. So it's nothing kind of unique to quantum, which we'll see once we get there as well. So this exponential increase in the dimension of the probability vector when you combine individual probability vectors is something totally, completely classical, right? It's already happening here in the classical case as well when we use the tensor product to combine classical probability vectors. In fact, it's exactly this operation that we use to combine quantum vectors as well. So there's nothing special or uniquely quantum about joining systems using the tensor product between classical versus quantum. The dimension in both cases is exactly the same, the size of the dimension in this case, right? It's 2 to the n in this case, right? Not the 2 to the 2 to the n, but it's just 2 to the n. Now, one interesting observation to make, perhaps more non-trivial note, even though, so this implication was going kind of, if you've got two vectors, here is the construction to combine it to get a bigger vector, right? However, not all four-dimensional probability vectors can be written as a tensor product. Of two-dimensional probability vectors, like we did above. Right, and that's, again, perhaps from the probability part, it's something obvious, but you see that I can write down this vector. People throwing out entanglement already. At the moment, there's nothing entangling over here. All is classical. right? So I have half 1, 0, 0, 1. This is a classical probability vector. There's no notion of quantum entanglement for us at the moment. All that this above note is saying is that this vector cannot be written as a tensor product of PQ tensor RS, which is the vector as we wrote PR, PS, QR, QS. And I welcome all of you who haven't thought about this before is to try to verify this, right? So you just observe that, hey, if I note that these two entries have to be 0, well, if these two entries have to be 0, that means these two entries have to be 0. That means either P or S is 0 or Q or R is 0, right? So either P or S has to be 0 or Q or R, one of them has to be 0. But then when you follow through with the logical implications, you require these to be half as well, and that just doesn't work out, right? So you verify that indeed this vector cannot be written as a tensor product of these vectors. Now, mathematically, coming in from probability, perhaps, especially if you combine that with the excuse me, the way you calculate probability in sample spaces, it might not seem that weird, right? So all that we are saying is that these two random variables corresponding to the probability vectors that we had were independent. This is, again, so I see lots of comments in Discord about entanglement and Bell states. Here we are not talking about entanglement at all. This is completely classical. And I'll try to say a bit more today and tomorrow again about this. This is not a Bell state. This is just a classically perfectly correlated system. Because it's correlated, the two random variables are not independent. Hence, you cannot write them down as probability of x1 times probability of x2. So that's like it's one of the more important subtle takeaways from this discussion, that this issue of two random variables being dependent or independent is something, again, obviously, that happens in classical probability as well. So the fact that you can end up with larger probability vectors that cannot be decomposed into smaller probability vectors, again, is something that happens in classical probability. It's not uniquely quantum. And we'll talk about more when we get to it, is what exactly is the distinction between larger quantum vectors that are said to be entangled, whatever that is, and classical vectors which are correlated, right? So the correlation over here refers to the fact that, in some sense, when you look at the system, either it's always going to be tails, or heads with probability half exactly. So that's the correlation between the two, right? Right. So someone asked whether you can think of the coins as being glued together. So I'll come to that point exactly when we do the quantum part, whether or not the two coins are glued together. In some sense, if you imagine doing two independent coin flips, then you do not expect them to be correlated, right? Because, well, they are independent. But the fact that two coin flips end up behaving in a correlated way means that somehow the two physical processes are connected. How they are connected, that's something that we'll get into later if time permits. But the issue is that there has to be some source of that correlation, how that correlation is being generated. We won't worry about how it is being generated at the moment, and just kind of just make this observation that indeed there is correlation here. And this correlation, though, has nothing to do with quantum. It's just referring to classical correlation. Is PR equals to RP? Is order important? Good question, Prithviraja. I recommend you kind of verify that, right? So to take two kind of probability vectors and take a tensor product and see whether they end up being the same thing or not, right? So take probability vector 1 and vector 2, combine the two together. Is that the same system or not? So most approaches that we're familiar with are kind of statistical in terms of finding out whether or not two probabilities or whether a given probability vector has correlation or not. There are statistical tests. That's a question that people deal with in terms of verifying whether a certain quantum process was actually genuinely quantum as well. It's a great discussion to have on Discord. I might not be able to get to it within this discussion, within these two sessions. All right. All right, so hopefully everyone is kind of okay with this note. Please keep this in mind, and hopefully we'll be able to kind of review it when we come to it. All right, just like we could define a combination of multiple probability vectors. Similarly, we could also combine multiple transformations as well. And it would happen as one might emerge in a similar way. If I have transformation A on the first vector, and if I have transformation B on the second vector, and let's say these are given by A1, A2, A3, A4 for A, and B1, B2, B3, B4 for B. How do I combine these two matrices together? Well, first of all, without even doing the computation, what's the size you would want for A tensor B, given that A and B both are 2 by 2 matrices? Four by four, yes, most answers 4 by 4. Total number of entries, obviously 16. Good, very good. Nice, people are following along. Kronecker product for tensor. Not 16 by 16, 4 by 4. Right, why 4 by 4? Because we just verified that when we combine two two-dimensional probability vectors, the resulting vector is a 4-dimensional vector. So it pretty much follows that, you know, the transformation then I should be applying on the corresponding physical vector for this physical system should be a 4 by 4 transformation. And indeed, that's exactly what the definition gives us. One nice short form way of writing it is, hey, this is just the scalar A1 multiplied with the entire matrix P, scalar A2 multiplied with the entire matrix P. You get the idea. Right, so that's your 4 by 4 matrix for getting your combined transformation. Note, even though the way I've written it, one might be thrown off that, hey, this is 2 by 2, but this is really a 4 by 4 matrix, since each B itself is a 2 by 2 matrix. Good, so we automatically get the notion that we've got larger transformations to correspond to the same dimension as the probability vectors that they will be applied to. Now, is the combined transformation first applying A and then B? Actually, the order in some sense wouldn't really matter, because because you're applying it on different systems, right? And because it's a tensor product, you can kind of write them out separately. It's kind of an independent transformation. A is getting applied on system X1, B is getting applied on system X2, and because they can be written as a tensor product, they are really independent transformations, and so you can indeed do them independently. Excellent kind of noting. However, if there was a transformation that you could not, if there was a 4 by 4 transformation that you could not decompose into smaller 2 by 2, 2 by 2 transformations, then we would get the notion similar to as we did in the previous case in terms of the probability vector, that, hey, this 4 by 4 transformation, if it cannot be decomposed into the smaller transformation of 2 by 2 matrices, then it's not an independent transformation, and it's kind of something that requires the two systems to be combined in some way. And so in there, the order kind of then would be dictated by how the transformation is combined together. And we'll see exactly an example of that, which is this operation over here, which some of you who are already familiar with what we are doing over here have seen. So it won't be an 8 by 8 matrix, right? So if it's not a tensor product, so for example, just like over here, we said there are 4-dimensional vectors that cannot be written as the tensor product of two two-dimensional vectors. Similarly, there are 4-dimensional matrices, 4 by 4 dimensional matrices, that cannot be written as a tensor product of two by 2 matrices. And one kind of very explicit practical example of that is the C0 matrix, which is also called the controlled, the C is for controlled, not matrices. So the not we already have seen is the negation operation. The control here is referring to the fact that when we visually represent this operation, so first of all, what's happening over here? I've drawn a small circuit. Time travels left to right, as is the case for all classical computation or computation circuits that are usually drawn. I've got 2 bits coming in, X and Y. This filled in circles identifies a control operation, and this filled in refers to the fact that this is controlled. This is the control bit. And this part over here means that this is the bit on which the not operation will get applied. And very quickly, this just says apply not on second bit if first bit is 1. So in some sense, the first bit being 1 or the first bit being switched on means that the control has been switched on. If the control is 0, then the control is off and nothing happens. So you see how there is kind of a connection that's been built into this operation, that what happens on the second bit is being controlled by the value of the first bit. And so it suffices for us to understand what this operation does on the 4 basis vectors, the standard basis vectors, right? So what are the standard basis vectors for 4 dimension? Right, so they'll just be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Now, it suffices for us to figure out what any operation does on the standard basis vectors to understand what it does on any other arbitrary vector, right? Because any vector, probabilistic vector, is just going to be a probabilistic combination of these 4 vectors, right? So, very good. I should write that this is the first bit, and this is the second bit. So, if I were to try to build, and some of you have already given it in the answer, but if you don't know the answer, let's quickly try to verify that. I want to come up with a 4x4 matrix that implements this operation. Let's figure out what this operation does directly on the standard basis vectors. Let's think of this matrix as n. If I apply n to the vector E00, well, what's E00? Well, that's this vector, E00. This is E01, this is E10, this is E11. Alrighty? So these are the 4 basis vectors. I am now trying to figure out what these basis vectors are transformed to under the operation n. So E00 is this vector, right? So what the 0, 0 kind of in the index refers to the fact that it implies that the incoming value is 0, 0. Well, what does the control not operation do? Because the control bit is 0, so the NOT gate doesn't get applied. So in this case, it acts like identity. E00 gets mapped to E00. Excuse me. And using the same reasoning for E01, because the control bit, the first bit, is still 0, nothing happens. I get the same vector as output. When the first bit is 1, what do you think will happen? Great. I'm sorry. E11. Some people gave the right matrix as well. Excellent. In this case, I get E11. And obviously, in this case, I'll get E10. All right. So in some sense, I've completely characterized the matrix N via these 4 equations. Excuse me. And in some sense, what I can do is to write down these 4 vectors directly in this matrix, and I've got the full transformation as well. So I write down 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. What comes next? Excellent, 0, 1, and then 0, 0, 1, 0. Note that each of the columns over here is exactly the output column that we identified over here. That's one way to look at it. Another way to look at it is that this submatrix is kind of the identity matrix, because that's exactly the identity mapping over here. And over here, you've got the NOT gate, because this is exactly the NOT gate being applied on the second bit when the first bit is flipped or switched on, or the control bit is on. Another observation to identify, and that I leave you to kind of work out, that this 4x4 matrix that we have just identified indeed cannot be written as a tensor product of these 2 such matrices. Why? Because here these 2 are independent transformations of 2 individual bits, Whereas this thing, as we've just seen, is not really an independent transformation, but it's really kind of a combined transformation. And the way we've combined it really depends on, well, whatever the construction of this operation was supposed to be. In this case, the logical construction was, if the first bit is 1, then apply a NOT gate on the second one. Right? Right. So Gaurav is requesting a break. We are pretty much done with the classical part of our conversation as well. So just give me a couple of minutes, and then we could take a 5-minute break. I hope that's okay with everyone. Right. I'll be able to get my coffee in as well, right? All right. So I know some people kind of, hey, where did this matrix come from? Let me quickly review that, leave you with a question as well, and then we'll take a 5-minute break. Hopefully everyone's okay with that. All right. Right. So where did this matrix come from? There are multiple ways to think about it, and each of them hopefully gives you a different input into this as well. One, well, people were able to verify these 4 equations. Hopefully, if not, just say, hey, this rule, if I implement it as kind of a condition on what this circuit or what this matrix is supposed to output, pretty much defines that, hey, the output of n applied to this vector will be this vector, and so on and so forth. Once I identify that, then you really have this observation that what I can really treat this matrices vectors as is really just these 4 output vectors. You write down these 4 output vectors in order for, hey, 0, 0 gets mapped to this vector. 0, 1 gets mapped to this vector. 1, 0 gets mapped to the 1, 1 vector. So no, this is the 1, 1 vector, not the 1, 0 vector, and so on and so forth. Where's a standard basis dimension for? Because in this case, we are working on a dimension for, right? So we were thinking about operation on 2 bits, and we verified in the previous slide that the dimension for 2 bits will be 4-dimensional. Is this a probabilistic transformation? Good question. What do people think? Is the controls not a probabilistic transformation in of itself? No, all right, it's a deterministic transformation, right? Sure, the input might be probabilistic, but the operation itself is really a very deterministic one. And you can kind of see that by looking at this. You can see that by noting that each of the vectors over here in the transformation itself are deterministic vectors. Right, so there are multiple ways to take that. Again, another way to think of it is, rather than if, let's say, we did not have these 4 equations, you could literally take this rule and directly construct the non-zero entries of this matrix. And the fact that we already know this characterization, that for a transformation, a classical transformation, each column is a probability vector, and we know that I get a 1 entry in each column, then all the other entries automatically will have to be 0, right? So there are lots of nice ways to think about getting, and so that's kind of one of the nice things that attracted me to quantum computing as well before. So you have this mathematical stuff in front of you, and there will be so many different ways of approaching that math and getting something else out of it. You look at it kind of a CS perspective, you look at it as a physics thingy, you look at it from a philosophical perspective, a material science perspective. And so going back to the starting joke from yesterday, there are lots of takeaways that you can have depending on how you look at it. Right? Alrighty. So for the 5-minute break, I leave you with this exercise. You don't need to answer right now. I won't provide the answer during the session itself as well. It's a nice little trick. And so assume someone hands you a biased coin. You don't know the bias, right? So it's a coin. So really think of it as a physical thingy, right? Your friend comes up to you, hands you a coin. You don't know the bias of the coin. You are guaranteed that it's not a fair coin. And it's also not a completely deterministic coin, i.e. it's not the kind that will always come up heads or to always come up tails. Now, the job for you is to figure out how you can simulate a fair coin using this biased coin. So come up with some kind of protocol that will allow you to simulate a fair coin flip using a protocol that you do, which may involve multiple flips if you like, or some other task that you may like. At the end of the day, you can write it down as a transformation. So what would be kind of the protocol that you would do where the input is a biased coin and the output is a fair coin flip? All right, and so we'll take a 5-minute break now. Hopefully, Marlou, that's okay. And we'll start in, let's say, what would be, in my case, 9:40. And so we'll have 20 minutes to get everyone up to speed on quantum information.
Yes, fantastic, and very well deserved to have a break. Let me see, there should also be a timer app, and then I can, okay, I turn it on. Can everyone see a timer in the back of my screen?
I can.
Okay, great. So then it is clear when the break will end. Feel free to take a break, everyone. In the meantime, Womanium team, please turn on your video if you're available for just some chatting and Q&A. And for those who don't need a break, then you can stay on, ask more questions, and have a chat with us. Saba is asking, is this session on YouTube live right now? Yes. Jasmine, can you please assist and share the link again on the Zoom chat and in the Discord chat? For everyone for whom it's going a little bit fast, no worries. This lecture will be posted on Canvas and Discord as soon as possible. Hopefully today, otherwise tomorrow. It will also include yesterday's lecture, so you will have both parts combined and can then go on with the exercises and quizzes. Let me share what is coming up tomorrow. 1 second to share my screen. There we go. Tomorrow and Friday. Tomorrow, we have first a game session coming up, Quantum Odyssey, and then the next lecture and a tutorial on QBronze. In this tutorial, Claudia from QWorld, Claudia and Deus Morales, will come to show you how to approach the exercises and how to actually program a quantum circuit and how to work with Qiskit. On Friday, we will have a keynote and a virtual lab tour in quantum computing at MIT, led by Will Oliver, professor at MIT, and Shantanu Jha. And then we will have the final QBronze lecture. Vardaan, could you share a bit more about this game, Quantum Odyssey, and also on Friday, Grover's algorithm? What is that and what is it useful for?
Sure. Yeah. Hey everyone, welcome back again. And I think you all deserve a 5-minute break. So I'll be very short in the description. You all should have received the link to download the game and install it in your local device. So it should be in your welcome email. It's Quarks Interactive, has provided a free license for Quantum Odyssey to everyone participating in the Womanium program. So that's an amazing opportunity for everyone to try that game. If you are not a part of the Womanium program, otherwise you would have to purchase that license, and we do not want you to go through all that process. We are making that available for free for everyone, all the Womanium scholars, everyone who's participating in this program. Do go through this module as Marlou is showing on the screen. Go through all the details, go through this team. Do make sure to like this and wish list this so that as soon as the updated version of this game comes, you are ready and you get all the updates. But apart from that, do download this game. This is an amazing opportunity. All the quantum stuff which you are going through the lectures, at least the fundamentals, you can also go through this game scenario, right? So in a very interactive and fun manner. You can learn what entanglement is, what qubits are, what superposition is, all the zeros and ones you have been talking about in the QBronze lectures. I'm pretty sure you'll get a very good interactive and more visualized feel during this Quantum Odyssey game. So this is completely on a self-paced stuff. There's no assessment for this game. You can do this on your own. You can find peers in the Discord chat and maybe schedule gaming sessions together, right? Just choose some slots during the day and compete against each other. Everything is possible. It's games, right? And if you do have any exciting news, perhaps you got a new high score or you're competing against yourselves, you want to share your snapshot, Discord is the way to go. So we'll be very happy to see any screenshots of that and your experience playing the game in the Discord chat as well.
Then on Friday, Vardaan, Grover's algorithm, what is that useful for?
Oh yeah, Grover's search algorithm, one of the capstone quantum algorithms. I'm sure many of the ones in the program who are already familiar with quantum algorithms. Grover's is one of the key algorithms one learns at the very beginning. So this is where a very fundamental algorithm which shows how you can use searching through a database much more quickly and efficiently using quantum stuff. I won't give you the spoilers just yet. I think you go through the QBronze tutorial and you'll get a better understanding of what I mean. But the good thing and exciting thing over here is that Erica Sturm would be giving this lecture, and she was a participant last year. Not only was she a participant in the Womanium program, she graduated the program, and now she is working as a QSL fellow. So all the QSL opportunities which I was talking about yesterday about the projects and everything, Erica Sturm is one of the fellows who was selected to work with the Naval Nuclear Lab. Today, she is working on one of the projects over there, and now she has been promoted to give a lecture to you guys on QBronze, which is a huge achievement for her, and we as a Womanium team are very, very proud of her. And I think, yeah, you all deserve those kind of opportunities. So I'm very excited to welcome all of you to give lectures to next year onward.
Then there was a question earlier in the session with Olivia Lanes asking, is there anyone working on quantum computing for optimization problems here? Stay tuned for this. The next couple of weeks, we will dive into both gate-based models and quantum annealing. And then for the projects, this could be a potential project where you do quantum optimization for climate applications or others. Then a question to you, Jibran, while starting everything. Someone asked what kind of research work is currently going on in quantum algorithms. Can you give some insight on that?
Sure. So as some of the questions that were asked in the earlier session as well regarding quantum advantage. And so that's something that came out of NISC consideration. So the idea that a feasible large-scale quantum computer is perhaps some decades away, and people were interested in, could we get some kind of interesting advantage, interesting benefit using quantum computers today with whatever kind of technical hardware we have available today. And so one of the big open kind of research areas today in quantum algorithms would be to identify and build algorithms that you could run on current hardware. And so that's really something non-trivial, right? So it's not just saying, hey, I've come up with an algorithm that works on this theoretical being that exists, which is a feasible large-scale quantum computer, and then Shor's algorithm obviously does that. But now what I'm really looking at is, hey, there are these limited computational devices with inherent kind of restrictions because of the noise level and whatnot. Could I still do some kind of computation on these limited devices where I get an advantage in terms of the amount of memory I use, in terms of the amount of time the algorithm takes, in terms of the amount of energy needed to run the algorithm, or in any other measure of resource that one would be interested in optimizing? Could I optimize that resource in a better way through a quantum algorithm than by a classical algorithm? So that's, I think, one of the key quantum algorithmic problems. For sure, not the only one, but in terms of practical applications, that's the one of the key applications that people are interested in. On the other hand, similar other kind of tasks are, or related tasks are, someone comes up to you and says, hey, here is a quantum computer. Well, if it was really a large-scale quantum computer, you would be able to verify it by just running Shor's algorithm on it. But again, because of kind of inherent limitations that we don't have quantum error correction, how do I verify that a certain black box is indeed a quantum computer? So coming up with protocols, coming up with algorithms that allow us to verify whether or not indeed a computation being done in a black box is indeed genuinely quantum, for whatever that might mean. More on that by end of tomorrow. For sure, not everything, but at least getting introduced to the idea of what does it mean to be genuinely quantum. So algorithms that allow you to understand that exactly would fall within quantum algorithms as well, that people are working on right now. All right.
Yeah.
And hopefully by the end of tomorrow, I'll try to kind of summarize the distinction between what we think we can do with classical computers versus what we think we can do with quantum computers.
Great. And there was also a question by someone, I can't figure out how qubits are used. What are they actually? What will qubits be presented in, for example, an optimization problem? Stay tuned for that. And next week, we will have a keynote on quantum computing hardware. So then you will learn more what the qubits physically are. And then over the course of the next weeks, you will learn more about how then these qubits are used in computations. Over to you, Jibran, for the last minutes of the lecture.
Sure. All right. Yeah. All right. So 15 minutes crash course in the rule book for quantum mechanics in quantum computing. Not a tough job at all. All righty. Anyhow. Okay. Where am I? Here am I. Okay. So just a quick note on the question that I left everyone with. The right answer is definitely there in the chat. There are some kind of slightly right answers there as well. Quite a few people got it. So I'm thinking people who have taken bronze previously have been talking. Anyhow, if you don't have the right answer, and so one popular answer is like, hey, it's just the F matrix that we saw previously, half everywhere. No, the issue is, well, how do I practically implement as someone Ahmed already mentioned in the chat? Well, the only thing you have is this biased coin in your hand. How do I apply what would correspond to F on this vector? Right, so you have to come up with kind of an operational process, which indeed at the end of the day, you could think of it as a transformation, but it helps to think of it as really, well, what will I do with this coin? Okay, all right. So the job now in the next few slides is for me to convey to you how the mathematical machinery that we just introduced changes with the quantum rule book. And really, that's the way to think about it. The mathematical machinery that we had was defining for us one way to think about classical computing. Although, someone who's looking at it the first time would be like, hey, this is all just matrix algebra, where is programming, where is computation? Then that's, again, the fun part of theoretical computer science. It's essentially just math, in our case, linear algebra. All righty, so rule number one for us. As Marlou just mentioned, what is a quantum bit? Unfortunately, I will not answer for you the physical part of this question. What exactly is the physical system that corresponds to a quantum bit? What is the reality of it? Whatever that might mean, we'll talk about that a bit later. But we assume now that that physical system X that we have been talking about all day today, what if it's not a physically classical system, or I'm not modeling it using classical physics, but rather this physical system X is a quantum system? What does it mean for that physical system to be quantum? Right, so all that we'll do today in the remaining part is hopefully just identify the mathematical rule book. I will not at all be conveying to you the motivation or the physical machinery in terms of why that corresponds to what quantum mechanics gives us, or why quantum mechanics is correct. That's interesting discussion to be had and lots to be said about it. But what we are doing today is taking the quantum mechanics machinery as a given, and even from that machinery, just extracting 3-4 basic rules. That is all that we need to get started doing quantum computing. So the first rule, the central claim of quantum physics for us, is that when we are modeling our physical system X, that in the classical case was in 2 different levels, let's say. And in the quantum case, now we want to be able to say, hey, it's still in 2 different levels. Well, just quick recap. In the classical case, it was this vector P, let's say 1, 0, and with 1 minus P, 0, 1, right? So that's one way to write down the vector P, 1 minus P. And the only constraint is that P has to be greater than or equal to 0. This probability is replaced by an amplitude. Why? Again, that's what quantum tells us. That you take this vector decomposition, and this vector decomposition will look exactly the same, except that I will have a nice, fun Greek letter psi to represent it, because, hey, that's quantum. And rather than using P, I will have, again, alpha, a complex number. The vector remains the same again. And beta, the vector remains the same again. And alpha and beta are complex numbers. They're referring to the amplitude of the system. It could be a spin system, half system. It could be a spin 1 system. Again, that's kind of the physical detail that I will abstract away from. All that I will take here is, hey, I've got a 2-level quantum system. In this case, it will have amplitudes alpha and beta. Well, what exactly are these amplitudes? What are the restrictions on these amplitudes? And how are these amplitudes connected to probabilities? That's exactly what the second rule gives us, which is the Born rule. So the first rule of going from classical to quantum is change the probability to amplitudes. Probabilities were just this nice numbers between 0 and 1. amplitudes so far I've just identified as being arbitrary complex numbers. For sure, there will be a restriction on them. Where the restriction will come from is from identifying, well, how are these amplitudes connected to probabilities? Recall that previously I said that when we have this classical system X, whose probability vector I represent as a vector v hat, then when I look at it, I don't see P, I don't see V, I just see the symbol associated with, let's say, the head, or the symbol associated with the tail, with the corresponding probability P, or the corresponding probability 1 minus P. In a very similar way, the quantum rule book tells us that when you will look at this quantum system, the probability with which you'll see it in state 0 or state 1 is going to be connected by the absolute value, squared of the amplitude. But again, just a rule that we're taking from the quantum mechanics machinery. So if alpha was the amplitude, the corresponding probability becomes magnitude alpha square. If alpha was a complex number, a plus ib, excuse me, then I can just write it as the magnitudes as a square plus b square, which will be a positive number now, right? It's exactly a probability. And so, as some people are already talking about, well, what's the distinction between kind of classical versus quantum? As you can kind of take away from here, is that in the classical case, if you wanted to talk about what's the restriction, it's kind of preserving the L1 norm, right? So P plus 1 minus P has to equal kind of 1. Whereas in this case now, given the rule, which is called the Born rule, in terms of how the amplitudes are connected to probabilities, you get a slightly different rule, which is on the L2 norm rather than the L1 norm. If it doesn't mean anything to you, that's perfectly fine. But the point is, rather than just summing up the two numbers, the probabilities, in this case now we take the square and add them up. Now, a simplification for our current purpose, for the entirety of the bronze workshop, and indeed pretty much the nickel workshop as well, we will assume moving forward that these amplitudes are real numbers. It's actually surprising how much of quantum mechanics kind of still works out if you restrict the amplitudes to be reals. The reason why we are doing it, because it just simplifies this issue of taking the absolute value squared. You could right now just take the square of the real number. So moving forward, we will assume that the amplitudes are real numbers. So all the equations I will write down after this slide will assume that the amplitudes are real. Just for this slide, for the sake of kind of completeness in the introduction, I give it as amplitudes are complex, right? So that means a qubit, i.e. a quantum bit, is given by, well, that psi thingy, which is this alpha beta amplitudes, which exactly I can write down as alpha 1, 0 plus beta 0, 1. But now in a position to write down the restrictions. The restrictions will be that, well, the probability to see it in state 0, which is this alpha magnitude square, plus probability to see it in state 1, which is the corresponding entry for beta, has to equal 1. So this is the quantum normalization constraint rather than the standard probability normalization. Indeed, it is still kind of just the probability normalization, because this thing is a probability, this thing is a probability, and all that I'm saying is that the two probabilities sum up to 1. The key thing that's changing in going from classical to quantum in terms of the mathematical machinery is that we are taking the probabilities and replacing them with these amplitudes, and hopefully that resonates with our start of the session yesterday, that, hey, our nice superpower is the ability to manipulate probability, and that's what quantum is going to give us. And that's one thing, again, to keep at the back of your mind in terms of whenever you see something, you're learning something new about quantum, how is that thing allowing us to manipulate probability in a different way, in a richer way than allowed by classical physics? already to begin with, we see that, all right, when we look at a quantum system, the way the probabilities of what we see emerges comes from this Born rule, which is this taking the square root thingy, rather than just, hey, the probability is just a linear combination, right? So that's kind of a crucial thing. Don't get hung up about the complex part. Drop the I behind. For the entirety of a workshop, we'll work with real numbers. So alpha and beta in real numbers will be sufficient for us. But for sure, not all of quantum mechanics can be derived through this. So, for example, Shor's algorithm uses quantum Fourier transforms that requires complex numbers. So I'm not at all saying that everything in quantum computing can be done with real numbers, but a surprising amount of it can still be done. So now let's write down the definition again, assuming that we have these real definition for amplitudes, real as in real numbers. So when we restrict the amplitudes to be real, then our good old trig functions come in, and those alpha and beta can be represented as just cosine theta and sine theta. Why? We'll see the geometric visualization, if not by end of today, start of tomorrow. And because, well, this corresponds nicely to our trig identity as well. So you really get a nice visualization that a quantum bit with the amplitudes restricted to real numbers just corresponds to kind of a unit vector kind of moving around on the unit circle, right? And so what is quantum mechanics giving us for a quantum bit? Instead of a probabilistic combination, what we get for quantum is, the name is, we have a superposition. In which case, you might as well ask me, well, what do you mean? What is a superposition? If you ask me the mathematical question, well, I will say, well, this thing is a superposition for choices of theta. Well, mathematically, that's well defined, but what's the physical reality of a superposition? And for me, that's kind of the key underlying question about, foundations of quantum mechanics, quantum information. What's the physical reality of an object, a physical object, when it is in superposition? Now, this may or may not make sense to ask. Indeed, there are people who work in quantum information and quantum mechanics and say, well, that's a meaningless question. And there'll be others who will say, well, that's exactly at the foundations of what it means to ask whether or not quantum mechanics is even complete to begin with. Referring to a paper in 1935 by Einstein, Podolsky, and Rosen, asking whether or not quantum mechanics is complete. More on that slightly later tomorrow. But trying to get a better understanding of what superposition is, i.e., what do I mean when a physical system is an alpha 10 plus beta 01? Could I just say, hey, this is in state 0 with probability alpha square and state 1 with probability beta square? It's very enticing to say this, but as we'll see as we go along, the richer machinery of manipulating probabilities in quantum does not allow us to kind of restrict our definition or interpretation of this expression as just alpha probability alpha square 0 state 0 probability beta square state 1. It's something slightly more subtle, and hopefully I'll try to convey that in our discussions tomorrow. So some people asked, hey, can probabilities be negative? Note over here, we don't have negative probabilities, but the object, the mathematical object through which the probability is emerging, in this case, alpha and beta, cosine theta, sine theta, indeed can now be negative to begin with. And this ability for them to be negative is exactly one of the key kind of ways through which we understand quantum mechanics to be providing us this rich feature. Go back to your high school classical mechanics, constructive interference versus destructive interference. You could never have probabilities combining together to constructively or destructively interfere because, well, they are always positive. Now you could have probability amplitudes coming in with plus minus signs and canceling each other out, or constructively adding up each other. And so that allows for a whole new interference pattern, well, amplitudes adding or subtracting together, which was not possible using classical probability. And that partially, in our understanding, is the source of the power of quantum computing. There's much more to it, but suffice for our today understanding of that, right? Okay, I think given our time constraint, I should stop here. It's a nice place to stop, where we have now introduced the base rule of what it means to define quantum information, i.e. quantum bits. We saw the key rules that change, going from classical information to quantum information. Starting tomorrow, what we'll see then is how some of the key rules of, well, what happens when we combine multiple classical systems together? Well, what happens when we combine quantum systems together? Actually, not much will change. The mathematical machinery exactly the same, the operation I apply is exactly the same, but because the underlying object, the vector that I'm working with, is a different beast, the way I combine it, even though it's still the same, ends up giving me something very different than what the classical thing was as well, right? So that's something to look forward to tomorrow. And then if time permits, hopefully it does, we'll kind of see nice, interesting quantum protocols in place as well that will motivate to you why quantum protocols do something in a better or in a more interesting way than classically possible. Ideally, we should have seen that today, but because of our time issue, we'll see that hopefully tomorrow. Alrighty. Questions, queries, concerns that I missed? Very expensive. Right. So I think so. We'll talk a bit more about quantum interpretations tomorrow in terms of quantum foundations. And for sure, there are lots and lots of nice ways to talk about interpretations of amplitudes and quantum interpretations. The nice thing that I've taken away from those discussions so far, as most people in quantum computing put it, is like, rather than religiously adhering to one quantum interpretation, the better thing to do is to be a bit more pragmatic and say, hey, for my current task at hand, which interpretation helps me the most? And well, just take that interpretation and use it. If you get some mileage out of it, why not use it? Right? So what exactly do I mean by interpretation and whatnot? Hopefully that will become clear tomorrow. But essentially, we're just asking, what does it mean for this particle to be in superposition?
Great.
And kind of what I'll end with today is just, why should we ask that question when no one asked, what does it mean for a classical system to be in a probability vector, right? So we automatically have this understanding that the classical system or object is kind of its own thing, and the probability vector is a mathematical construction that we have for talking about it. Why should we not say the same thing about this superposition vector? So that's something we'll try to talk about tomorrow. All right, thank you. I'll stop there.
Great, Jibran. Thank you for a wonderful lecture. I see Ahmed from Turkey says, oh, we're stopping already. I wanted more. So that is great. And we will get more tomorrow. Tomorrow, when we will have 20 minutes game demo, then a lecture by Jibran, and then a tutorial by Claudia. If there are more questions flowing in, maybe Jibran has time to stay on for 2 more minutes. In the meantime, what about the materials, the quizzes, the exercises? First of all, a recording. We will work to get that online as soon as possible. The recording from yesterday's part of Jibran's lecture and today. Lecture slides, will they become available, Jibran?
I will just send it on, I will share it on the Bronze channel in program modules, like in 5-10 minutes after we end the Zoom session.
Great. So the slides will be available in 5 to 10 minutes on the QBronze channel and on Discord, and we will also edit on Canvas. The quizzes on QBronze that you can do on Canvas now is, of course, getting started. Maybe if you already did QBronze, you can upload your previous certificate. If you didn't, just do the quiz here and click no. And then what are the quizzes that people can complete further, Jibran?
So we've definitely covered the basics of classical systems, but I would strongly recommend working with the Jupyter notebooks first before starting basics of classical systems. So even though I've introduced the key information in the quiz. The kind of questions you have in the quiz are based on the kind of programming exercises that you do in the notebooks. So you would be much better prepared for the quiz if you go to the Jupyter notebooks for basics of classical systems. We'll go through them once and then approach the quiz.
And these notebooks,
but we've done the lecture content for it for sure.
Yeah. And these quizzes or these Jupyter notebooks you can find via GitLab. And then at least do these for classical systems. Okay. Great. Thank you very much, Jibran. We will see you tomorrow.
Thank you.
And
thank you.
We look forward to your slides and notes online. Thank you very much.
Thank you. Thank you, everyone. So maybe I'll take a brief break and then I'll answer any questions that are on Discord. Please feel free to post on the QBronze channel because the live questions, I think, ends as we finish the live session. So if you want a longer discussion, post your questions in the QBronze channel and I'll get to them. So, thank you.
Perfect. Thank you very much, Jibran. I will stay online for a couple more minutes to answer more questions. But the session has ended, so congratulations everyone on finishing day 2 of the program. Feel free to leave now, but also feel free to stay on if you have more questions or want to hear the answers to questions from others.